I want to emphasize again that because the information is ultimately broken down into questions of true or false, yes or no, 1 or 0, there's absolutely no ambiguity. There's no gray area. Either it's a 1 or it's a 0, and therefore there's no way of producing interference with this information. There's no way of degrading the information. There's no way, at least in principle, of anything happening but either a 1 or a 0 comes out, and the right thing comes out all the time, whatever you put in there. There's no shades of gray in between. Well, how does it work on a CD or DVD? Well, on a commercially made CD or DVD, like the one you're watching from this course, if you're watching this course on DVD, or like this music CD, the information is actually stamped into a little metallic layer on this plastic on the disc, and it produces little tiny regions called pits, little holes, if you will, in this little tiny metallic information layer. That's done because that's a very robust method. It's a mechanical deformation, literally, of the disc. That's why we say we talk about stamping discs. We also talk about burning them, and I'll get to that later. That's a different process. But commercial discs are literally stamped out in these little pits. Now, these pits are tiny. They range in size from an order of 1 to 3 millionths of a meter. A human hair, by the way, is 100 millionths of a meter in diameter. So we're talking about things that are about 100th of the diameter of a human hair. And these pits extend in a spiral track. They're about 1.5 millionths of a meter apart, and there are spiral tracks that run all the way around the disc. There's about 22,000 of them. If you laid them out straight, the total number of tracks on an ordinary CD would be about 3 miles long. Remarkable device. And the number of those pits determines how much information you can store. So it's the number of those pits that you can cram in that determines that we can store about 74 minutes of music on a typical CD, and we can store about 640 million bytes of computer information on basically the same CD. By the way, as you look at a disc from the bottom side, the business end of the disc, if you will, not the side with the label, you see these rainbows flashing off. You can't see the pits themselves. They're too small. But those rainbows are evidence that the pits are there. Why do they occur? We'll get to that in the next lecture. Let's take a look, though, at what a close-up of a CD would look like. So here's a CD, picture of a CD. Took that picture just by putting the CD on a scanner and scanning it. And if we blow that up, many, many fold, there's a little tiny spot of the CD. Let's blow that up. We see something that looks like this. This is a picture that shows a hunk of the CD, a little tiny piece of it. You see here 3 parallel tracks in those spiral tracks that are going around the CD. You see several pits. Some of them are longer, some of them are shorter. They come in various sizes. Some of the smallest are these little round ones, and there are longer ones. The red or orange spot in the middle is roughly the size of the laser beam spot that's reading the CD. So that's how that works. That's what's going on there. A laser beam shines on this. How does a laser beam work? Well, we're going to get to that in lecture 34. And these pits appear not because they're stamped from above, they actually appear as little raised areas. And the laser beam shines off these raised areas, and it reflects. And when it hits a flat area between these pits, all the light gets reflected off. But when it hits the edge of one of these pits, for reasons that we'll cover in more detail in the next lecture, but I'll give you a hint of now, some of the light is reflected, but some of the light interferes with itself and diminishes its level. So here's roughly what it looks like. Here are a couple of these tracks of pits. We're looking down on the top of the disc, and we shine a laser beam, and that laser beam bounces off the CD, and how it bounces depends on whether it's on a pit, on the space between a pit, or on an edge of a pit in between. You might think, by the way, well, we're going to let these pits represent digital 1s and the non-pits represent digital 0s or something, but actually we let the pit edges, the edges represent 1s and the blank space in between represent 0s, and there's a clever coding scheme that makes sure we'll never be ambiguous about this. So what happens? Well, this is a top view. Let's take a look at a side view of what's going on here. So here's a side view of a disk, and what you see here is at the top the disk surface where the label is attached. Actually, only a short distance down below that, and this disk is quite thin. It's about a millimeter and a half thick. It's quite thin. Down just a little ways from the top is the metal information layer in which those pits have been stamped, and I've suggested that here in this drawing by the depth of the pit. And then underneath there's a fairly thick layer of plastic, thick plastic underneath that basically protects that information layer. In a sense, the disk is actually more vulnerable from the side with the label than it is from the side below where it's red. So what happens? So we shine laser light on the disk, comes up through the bottom of the disc, through that transparent plastic, it bounces off, and out it comes and is picked up by a photodetector of some sort in the CD player, and that information is sent to electronics that decodes it. That's what it looks like when it hits the part of the CD between pits. Here's what happens when it hits a pit edge. Some of the light bounces off the flat part below the pit, some of it bounces off the pit itself, and notice what's happening here. Those two light waves have come out, and they are out of step. One of them has had to travel a little bit further, and as a result, for reasons I'll describe in much more detail in the next lecture, they interfere with each other, and the light is dimmed. So that is how the information has gotten stored. We have dimmer light when the pit edge is underneath the CD. And so that's basically how a CD works. And I want to show you, before I go on to talk a little bit more about the properties of these CDs, I want to show you a simple demonstration of exactly what's going on here. What I have here is a device a student of ours actually built. It was sort of a model to show how a CD works. And here is a real CD, which the student took and marked with big hunks of black magic marker to simulate the effects of these pits. Now, these things are probably 100 to 1,000 times the diameter of a human hair. And since a human hair is about 100 times the diameter of the pits on a CD, these are probably 10,000 to 100,000 times bigger than the pits on a real CD. What I have here is a little demonstration he built in which we took the motor out of a real CD drive. So that's the motor out of a CD drive, and I'm going to plunk this fake CD down on it. I have, instead of an ordinary laser, I have a laser pointer here, standard laser pointer for pointing at a blackboard, shining down on the CD, and I have a very tiny photodetector which will detect that, and the electrical signal from that photodetector is going to come out of this cable. And I'm going to look at it on a device. What I'm going to do is plug into the oscilloscope the signal coming from the CD, the pseudo CD player. I'm going to turn it on and get the disc spinning. And I'm going to look at a signal. Now, because the screen on this particular oscilloscope is fairly small, we've set up a larger screen connected to the oscilloscope and seeing exactly the same thing its screen does. And we'll put that on your screen for you to see. We'll put that on the recording we're making. So I'm looking at this screen, but you're looking at an identical but larger screen that will film better. And you see a pattern of low levels and high levels. Low level there, short high level, low level, high level, low level, high level coming up. And if I take another shot at this, I'll catch it at a different part in the disc, and you see a slightly different pattern corresponding to the different sizes, the different lengths, the different times those different dark and light patches are on. So there's a pattern for a different part of the disc, there's something different, there's something different, there's something different. And the time scale here is fairly long, a matter of a good fraction of a second. On a real CD, if I were doing the same thing and looking at the raw data that were coming off the CD, I would be working at thousandths of second time scales or tenths of thousandths of seconds in order to see the same kind of thing. You might say, what does this silly fake CD sound like? Well, I can connect a microphone, a loudspeaker up to it, and you will hear that. It's not very dramatic. It isn't going to be Brahms' Third Symphony, but here's just a little loudspeaker which I will connect up. So that wasn't very exciting, but what you did hear at least was some variation in the sound. It wasn't just a monotone, and that variation corresponded again to the variations in the sizes of the pseudo pits that my student has written on here with black magic marker. By the way, if I connect the loudspeaker again, and turn the device off, you hear it slowing down just as you might expect, something you don't hear from your usual CD player. So CDs are great things, and by extension DVDs are great things, and this is basically how they work. One huge advantage of CDs over previous storage systems is they're enormously immune to dust. You might think, if I'm dealing with these pits that are a millionth of a meter in size, what if I get a tiny speck of dust on the thing? How come that doesn't throw the whole thing off? If I got a tiny speck of dust on my phonograph record, it makes a scratch or a blip or something that I hear in the played music. Doesn't happen with a CD. Why not? Well, the reason it doesn't happen with a CD is because of the way that information layer works. Okay, so here's a picture. This is not to scale. At the top you see the information layer where those pits are stamped. That's where the information is stored. And you see just a slight variation in that layer that represents the pits. Down at the bottom is the lower edge of the CD. And we're going to shine laser light on that. Now it happens that the laser beam coming in looks something like this. It's quite wide at the place where it enters the CD. It's about 1 millimeter wide, about the width of those smallest divisions you can see on a meter stick. It's being focused by lenses that you don't see here in this picture outside, so it's coming in that conical kind of shape. You'll notice that it enters the disk, and then the path of the light rays change, and they do so by the process of refraction. We'll cover it in a subsequent lecture and understand how that works. And this is very carefully engineered, and the plastic of which those disks are made has to have exactly the same optical properties for all disks, so that the laser beam, again, this is not to scale, is focused down on the information layer to a size on the order of 2/1000ths of a millimeter, about 2/millionths of a meter. And you saw that on those previous pictures where I showed you the size of the laser beam against those pits. It was a little bit bigger than the pits. It was about 2/millionths of a meter. And so if I were to have a speck of dust, even a pretty big speck of dust, a good fraction of a millimeter in size, land on the CD, would have very little effect. It might cut down on the intensity of the laser beam a little bit, but unless it cuts down so much that it becomes ambiguous whether the reflected light off the disk represents a 1 or a 0, no problem at all. So these disks are remarkably immune to dust, unlike old-fashioned phonograph records. Let me end up simply by saying that these CDs and DVDs that are very much a part of our everyday lives are amazing devices, and they're made possible with the application of a whole host of physics principles, especially in the fields of waves, optics, a little bit in mechanics, a little bit in sound.